Okay, class, in this video we're going to talk about the characteristic equation for a second order linear differential equation, and I should say the homogeneous differential equation. So we're going to say that if ay double prime plus by prime plus cy equals 0, which I'm going to refer to from now on out as star, the generic non-homogeneous equation is going to end up being star star. So just for future reference, that's what's going to happen. So the characteristic equation, so what do? We change the y's to r's, and we change the primes to a power that's the same degree. So ar squared plus br plus c, notice y is y to the 0 derivative, so c, no r, is equal to 0. That's just a quadratic equation, right? So really, the take-home message here is that everything in terms of these types of equations boils down to solving a quadratic equation. All right, so I'm gonna prove a couple theorems here, and they're going to relate to how we're going to solve things, but not necessarily everything. So we're going to say that R1, we're going to let R1 be a solution to AR squared plus BR plus C equals 0. Okay, so that's the beginning part of my little theorem here. Now what does that mean? That means when I plug R1 into the left-hand side, I get 0. Okay, that's important. Okay, so if that's the case, then e to the R1x is a solution to my homogeneous equation. Okay, now how do we prove something is a solution? We plug it in. So here's the proof. We're going to let phi equal R1 e to the R1x. I'm sorry, e to the R1x. Okay, the derivative of that chain rule is R1 e to the R1x. I was getting ahead of myself. And then when I take a second derivative, another chain rule, so phi double prime is R1 squared e to the R1x. All right, so let me substitute that in. Okay, so I'm going to substitute that into star, which means A phi double prime plus B phi prime plus C phi equals, okay, I can't set it equal to 0 yet. I have to show that it's equal to 0. So I'm not setting it equal to 0. Notice that. All right, so I'm going to substitute these guys in for phi's. So this is A R1 squared e to the R1x plus B R1 e to the R1x plus C e to the R1x. Okay, so that's just me substituting that in. And then typically what happens with these guys, you regroup. Okay, so how am I going to regroup? I notice that all three of these terms have an R1x in them. So if I factor that out, e to the R1x, sorry. So if I factor the e to the R1x out, I'm left with AR1 squared plus BR1 plus C. Okay, now remember what my supposition was back up here. R1 is a solution to this. That means when I substitute into that, I get 0. And lo and behold, that's R1 substituted in. So all of that is equal to 0. So the whole thing is 0. So I've just shown that when I plug that function into the differential equation, it equals 0, so it satisfies the differential equation. So it's a solution. Okay, so another theorem. Let's say let R1 be a double root, oops, spelling double wrong, double root of AR1 or AR squared plus BR plus C equals 0. Okay, so what do I mean by double root? So first of all, let me finish the theorem. So then I'm going to claim that x e to the R1x is a solution to star. Okay? All right, so that's going to be a solution to the differential equation. Now, let me come back up to here. So if I just look at that quadratic equation and sort of break this down, I can use the quadratic formula and I get minus b plus or minus the square root of b squared minus 4ac over 2a. So that's my quadratic formula. And if it's a double root, what happens, if it's a double root, we don't have this plus or minus deal, meaning b squared minus 4ac is equal to 0. So that means R1 in this case equals minus b over 2a. Okay? And the implication there, so we need to go a little bit further. So typically what people mess up on here is they say b squared minus 4ac is 0, and they actually need this. So I'm claiming R1 is a double root, which means that automatically has to be 0. So if I rearrange this, if I multiply by 2a and add b, I get that 2a R1 plus b has to be 0. That's always going to be the case in a double root. So, back over here. So my proof, I'm going to let phi equal x e to the R1 x. Then phi prime, this time I have to use product rule. So this is e to the R1 x plus x R1 e to the R1 x. That's chain rule. Okay, so that's phi prime, phi double prime, R1 e to the R1 x, and take the derivative of x, once again product rule in this part, so R1 e to the R1 x plus x R1 squared e to the R1 x. And I'm going to try to fit this on this sheet of paper, so we'll see how that goes. That's simplified down. That's 2 R1 e to the R1 x plus x R1 squared e to the R1 x. Okay, so a phi double prime plus b phi prime plus c phi, what is that equal to? That's a 2r1 e to the r1 x plus x r1 squared e to the r1 x. Okay, I have to move this way a little bit. So b e to the r1 x plus x r1 e to the r1 x. And then, once again, I'm running out of room, plus c x e to the r1 x. Okay? So this is what I get when I plug that in. Now, I'm just going to take that and I'm going to simplify. So what I'm going to do is I'm going to look for like terms. So I've got two types of like terms. I've got x e to the r1 x's, and I've got e to the r1 x's. So let's start with the x ones. So I'm going to have an a r1 squared when I factor it out of that term there. And I have an x r1 e to the r1 x there. So when I factor the x e to the r1 x out of the middle term here, I'm going to have plus b r1, and then I just have my one term there, so plus c. What's left over? In the first term, I have this e to the r1 x, so I'm going to factor that out. And I would have 2a r1, and then the second term would have the b. Okay, now let's see where we are. We're hoping this is all equal to 0. So we know, since it's a root, that when we plug it into the characteristic equation, we get 0. So from our first theorem, we know this is 0. And then we said it was a double root, and look at the condition we ended up with. 2ar1 plus b equals 0 if we have a double root, so that makes this part equal to 0. So poof, the whole thing is equal to 0, and that means that that is a solution right there. That's a solution to the differential equation. Okay, if we have a double root. Okay, let's stop there, and then we'll look at case 1, case 2, and case 3, and we'll be ready to solve some.